Hi, so today I wanted to talk a bit about analyzing MIPI DSI display initialization, particularly for displays which you may not have documentation for and you still want to reverse engineer and use. So for example, I have this 6-inch flexible OLED panel from BOE. It's 2880 by 1440 pixels, and it has a standard 4-lane DSI interface. This was used in at least one phone around 2018 from Huawei. But these are available, for instance, on AliExpress and actually Amazon in the US currently. But there's no datasheet for this particular panel that I can find. You can only purchase it typically just as the bare panel or with one of these driver board kits, which provides HDMI to MIPI DSI conversion, and then since this is a standard board, they give you this little adapter which has the requisite OLED power supply and connector for the particular display they're selling it with. So if you want to buy one of these sort of obscure displays from some seller in China and want to use it in your own project, you're kind of stuck just with this little board as an example of how to use it. Now, from the electrical point of view, of course, there are considerations there, and I've, in this case, designed my own complete system here, which can connect to this display. But specifically, I wanted to talk about sort of the digital protocol side of things and how these displays are initialized. So, since there's often some driver-specific initialization commands that need to be sent over the interface before the display will work in video mode, you either need to ask the seller if they have that sort of documentation or find it online somewhere, maybe in some device trees or info from Linux source dumps that people have published for various phones and such. Or you need to find a way to reverse engineer it out of these driver boards that you do have, which are a working example of initializing the display. So I've come up with several situations where I've wanted to do this, and so I wanted to show how I've been approaching it. And of course, this is also useful if you've designed your own system, which does send these initialization commands, even perhaps for a display that is documented, and you'd like to analyze them over the bus. Perhaps your display isn't working at all, you want to see exactly what's going on. So I wanted to explain how I've been doing this. So specifically, I'm talking about these low power mode commands, the low power data transmission that happens often before you set the link into high speed mode and are sending video data on all 4 of the DSI lanes. So in this particular setup, I've connected both the P and N, positive and negative sides of the differential pair of data lane 0, which is where this low power data transmission is going to happen, to a logic analyzer, in this case the analog discovery 2, and I have waveforms here. Now certainly you could use other logic analyzers, but this waveforms I find to be very convenient just because of all of the scripting capabilities it has and capabilities for data export. So essentially, I have my system here powered by this power supply. So I can start it up, and then what I'm doing here is using the logic analyzer in record mode so that the computer's memory is used as its sample buffer, and the samples are continuously streamed over USB, so you can record for a longer period of time. So currently there's nothing here, but if I start up this system and then time it right so that I hit record when the system will start transmitting this initialization data, I can capture it on data lane 0 before the lanes go into high speed mode and start transmitting video data. Now, of course, you can learn from the DSI spec, of course, that this transmission happens with 1.2 volts signaling, essentially, this low power mode. So the analog discovery 2 is capable of capturing this just fine in 1v8 digital input mode. The analog discovery 3 removed the 1.8 volt digital input mode, which I think is a very misguided decision, but anyway, that's what digital is doing nowadays. So if I turn on the power here and time this just about right. We'll see if we can capture when that initialization happens. There we go. So I'll just turn the system off now. So this is a system that I designed, but in fact it wasn't working to start up this display, so I wanted to diagnose what's going on here. So you can see when both lanes go into LP11 state here, and then before data transmission happens there, which of course is kind of all messed up and unusable because this is, this is just a normal logic analyzer not set up for any differential stuff. Before that, you can see low power data transmission here. So there's this characteristic escape mode entry here, which ends right about there, and then this is least significant bit first. So from MSB to LSB, it's 100000111, which is the low power data transmission entry byte essentially, and then from there on you have data. So I guess some high-end scopes have this decoding capability built in, but if you don't have a high-end scope, you can, in waveforms or potentially any other logic analyzer you're using, you can get the raw data and export it as a CSV. So essentially I've done that and then written a script in Python to just import that and decode this easily for you to see. So that script looks like this, and essentially it just looks for that start, then goes along shifting the bits in, and when it sees both ends of the differential pair go back into LP11 mode, when it's finished over here, the escape mode, well, it finishes the data transmission and you're back in LP11 state, then it considers that the end of a transfer essentially, and it'll print out the next one's on a new line. So when you run that sort of script, I already did that export into this CSV file. It will just load it up using NumPy and then run through it and do the decoding, which will just take a moment. And that is the data that's being transferred. So for instance, hex 39 is the DCS long write command. Hex 15 is that's DCS short write with 2 parameters. Hex 5 is this single parameter thing which is used for like setting the power modes. So this I found really helpful because not only did I use this as a tool to even find these initialization commands for this undocumented display, that's where this came from in the first place. Now I'm using it to diagnose this system that I'm designing to see what's going on. So I did find some mistakes, like I incorrectly interpreted this data from the original reverse engineering run, so I have to fix that. These are not right. This at the end is coming from the backlight system. There's some additional backlight code I left in there in my Linux driver, which I'm probably going to remove for the time being to make sure this isn't causing any issues. Just for an example of where I'm applying this, this is the driver that I've been just toying around with to work on this display that I put together. So it performs those writes here, and you can see I've already fixed these and changed the data to the correct values. So yeah, perhaps this sort of approach can be useful for people trying to reverse engineer displays. I'm not sure if there are other tools currently available for doing that, but it's not very difficult at all to write a little script to do this. And of course it is on my GitHub page over here. Oops. Yeah, it's in my DWF scripts repository if you'd like to take a look at it. And yes, if you had a logic analyzer, for instance, like the Discovery 3 or something that only handles 3.3 volt inputs, of course you just have to, put some level shifters in front of it. I suppose even with a microcontroller like an Arduino and some level shifters, you could pretty easily receive this. But yeah, the Discovery 2 makes it really easy with the 1v8 analog input or any other analyzer that can handle these input levels. Hopefully you might find that interesting, and see you later.